Pluto is one of the coldest and most distant worlds in our solar system. But for years, scientists noticed something that didn't make sense. Its atmosphere was dramatically colder than their calculations predicted, by roughly 30 degrees Celsius. That difference was far too large to simply blame on an instrument error or a minor mistake in a computer model. Something important was missing. Then James Webb Space Telescope looked at Pluto in a way previous observatories couldn't. And the result provided strong evidence for an idea that had been proposed years earlier but was initially considered extremely unusual. The surprising culprit wasn't a powerful greenhouse gas. It wasn't an underground heat source. It was a layer of microscopic particles floating through Pluto's atmosphere. And those particles may be controlling Pluto's climate. To understand why this is so surprising, we need to go back to 2015. That was the year NASA's New Horizons spacecraft finally reached Pluto after traveling for more than 9 years. Before that encounter, Pluto had mostly been a tiny point of light. Even the best telescopes could reveal very little about its surface. Scientists knew it was small, frozen and incredibly far from the Sun. Many expected a relatively inactive world covered in ancient ice. Instead, New Horizons discovered something completely different. Pluto had enormous mountains. It had vast plains covered with nitrogen ice. It showed signs of geological activity. And surrounding the entire world was a thin atmospheric haze. The haze extended hundreds of kilometers above the surface and created the faint bluish appearance that became one of Pluto's most recognizable features. But the haze wasn't the biggest mystery. The real problem was temperature. Scientists already had models that could estimate how cold Pluto's atmosphere should become based on the weak sunlight reaching the dwarf planet and the behavior of its atmospheric gases. The predictions produced one answer. The spacecraft measurements produced another. The atmosphere was much colder. The difference was around 30 degrees Celsius. For a planetary atmosphere, that's enormous. It suggested that some physical process was removing energy far more efficiently than existing models had assumed. Researchers spent years examining the measurements and testing possible explanations. Then, in 2017, planetary scientist Shi Zhang and colleagues proposed an unconventional possibility. Perhaps Pluto's haze wasn't simply something that happened to be floating in the atmosphere. Perhaps it was actually helping determine the temperature. The idea was fascinating. Ultraviolet sunlight interacts with methane high in Pluto's atmosphere. Those reactions create increasingly complicated organic molecules. Eventually, tiny solid particles known as tholins form. These particles slowly descend through the atmosphere and contribute to Pluto's famous haze. But according to the proposed mechanism, the particles could do something much more important. They could absorb energy and release it at infrared wavelengths. In other words, the haze could act like a microscopic radiator. Instead of simply reflecting or scattering sunlight, these particles could help carry thermal energy away from Pluto and send it into space. That would provide a natural explanation for why Pluto's atmosphere was so much colder than expected. But there was a problem. A scientific theory isn't enough. Researchers needed an observation that could actually test the idea. And the prediction was very specific. If the haze really was responsible for this cooling, it should produce a detectable infrared signature. The challenge was that the signal would be incredibly faint. For years, scientists didn't have an instrument capable of separating it clearly from the rest of the Pluto system. Then James Webb arrived. Launched in December 2021, Webb was designed to study extremely faint infrared light from across the universe. One of its most important instruments is MIRI, the mid-infrared instrument. And that was exactly the kind of instrument needed for this problem. In observations conducted in the early 2020s, researchers used Webb to study Pluto and its largest moon, Charon. This was technically difficult because Pluto and Charon appear extremely close together from Earth. Earlier infrared telescopes could detect radiation from the system, but separating the contribution from Pluto from the contribution of Charon was much harder. Webb's much larger mirror and advanced infrared capabilities changed that. Researchers could analyze the infrared emission from the two worlds with much greater precision, and the results were remarkable. Pluto's infrared emission couldn't be explained simply by radiation from its frozen surface. There was an additional component consistent with emission from its atmospheric haze. That was exactly the kind of behavior the earlier haze cooling theory had predicted. The particles weren't merely creating a beautiful blue atmospheric layer. They were apparently participating directly in Pluto's energy budget. The findings were published in 2025, providing important observational support for the idea that Pluto's haze plays a major role in keeping its atmosphere unusually cold. And this changes the way scientists think about Pluto. For a long time, planetary climate models have primarily focused on gases. Earth's atmosphere, for example, is strongly influenced by gases such as carbon dioxide and water vapor. Other worlds have their own atmospheric chemistry. Titan's thick atmosphere contains methane and nitrogen. Venus has an enormous carbon dioxide atmosphere. But Pluto offers a different possibility. Tiny solid particles suspended in an atmosphere can become an important part of the planet's climate system. That is an extraordinary idea. And the chemistry behind those particles is equally fascinating. Pluto's upper atmosphere contains methane and nitrogen. Solar ultraviolet radiation drives chemical reactions involving those molecules. The resulting compounds become progressively more complex. Eventually, they form the dark organic material known as tholins. These particles can scatter visible light, contributing to Pluto's hazy appearance. But they can also interact with infrared radiation. That gives the haze two very different roles. It helps create what we see. And it helps determine what we don't see, the heat escaping from Pluto into space. The story becomes even more interesting when Charon enters the picture. Pluto and Charon are unusually large compared with one another. Their relationship is so unusual that scientists sometimes describe the pair as a binary system. Charon itself has essentially no substantial atmosphere like Pluto's. But material can move from Pluto toward its moon. Methane escaping from Pluto can eventually reach Charon's surface. Once there, sunlight can drive additional chemical reactions. Those reactions can create reddish organic material. That may help explain the striking red region near Charon's north pole. So Pluto isn't completely isolated. Material from its atmosphere can travel through space and alter the chemistry of its neighboring moon. It's an extraordinary example of two distant worlds interacting as a system. And Webb's observations made it possible to study that interaction with much greater detail. The measurements were made across infrared wavelengths far beyond what human eyes can see. MIRI is particularly valuable because Earth's atmosphere blocks much of the mid-infrared radiation that astronomers want to observe. By placing the instrument in space, Webb can detect these faint thermal signals without having Earth's atmosphere interfere as strongly. Researchers can also observe how the infrared brightness changes as Pluto rotates. That provides information about surface temperatures, thermal properties and atmospheric contributions. This is something New Horizons couldn't easily accomplish. New Horizons was designed primarily for a rapid flyby. It reached Pluto in July 2015 and had only a limited amount of time to collect data while moving past the dwarf planet at tremendous speed. Webb, by contrast, can return to Pluto and observe it repeatedly. That difference is extremely important. New Horizons gave humanity our first detailed look at Pluto. Webb is allowing scientists to monitor the world from a completely different perspective. And Pluto itself turned out to be far more complicated than anyone expected. One of the most famous discoveries from New Horizons was Sputnik Planitia, a gigantic region dominated by frozen nitrogen. The area is enormous, roughly comparable in scale to a large U.S. state. New Horizons also revealed mountains composed primarily of water ice. At Pluto's surface temperatures, water ice becomes strong enough to behave more like rock.